let's record. Yeah, it's pretty much up to you two. What you'd like to do.
I don't know what I'd like to
do. Zoe, do you have any strong preferences on? I know that you use Agda quite a bit, so you may well be more expert than us.
I don't think so.
Is there anything you'd like to cover in particular, or I guess we could do some practical examples. I don't know.
How far did you get in the previous meetings? Because I think I've missed some.
So I think we are at the end of section 5, right?
Well, so I don't think we.
Oh, we didn't quite get there.
We went a little bit off on a tangent last time, and we didn't really talk a lot about how the book structures isomorphisms and embeddings. So this was sort of what we were looking at, but I think we went a little bit off on a tangent on lambdas and what they can express in Agda, that sorts of things.
Yeah.
So this is one thing we could look at, and there's possibly some things that we could talk about that relate to this, and how because what the book does is maybe not as standard, or maybe not necessarily what happens in the standard library, and there's some concerns that we could talk about there.
Yeah.
So if that's something that would interest you guys.
Yeah.
For some book, yes.
So yeah, you kind of mentioned it.
Or the alternative is that we could do some small practical thing. We could try and prove the pigeonhole principle or something, like as a practical, as I see it. So people prefer the book is Untitled Chapter book. Zoe, are you okay with that?
Yeah, this everything's good with me.
Okay.
But we should also record it.
It's recording. I have remembered, but thank you so much for reminding me, because it's pretty much the first time I have remembered to record it. So yeah.
So we stopped. It has been a while. Maybe I have something as well. So basically, we stopped at isomorphism.
Yes.
Yes. So last time we looked at isomorphisms, but we sort of got sidetracked by some aspects of what they were using.
Yeah, James is talking. I'm sorry.
Yeah.
Maybe he was coming and then some
Got distracted. Okay.
Yep.
Hey, come in.
Hello.
Okay, so remind me, where did we get up to then?
So
Did we
I
talk
think
about
we looked at extensionality, and I think we got sidetracked by lambdas at some point.
Okay.
And we dived deep into what lambdas can do in Agda.
Oh yeah, pattern matching lambdas. Yeah.
Yes.
Yeah.
And so we didn't really. I don't think we ever. Maybe we looked at the isomorphisms a little bit, but not in too much detail, I don't know.
Okay then.
So yeah, so this is how the book defines isomorphisms, and this is the first time that it uses records. So I think we talked a little bit about what these are, right? These are sort of like single constructor data types, but with named fields. And they are nicer to use oftentimes when you do have a single constructor, because these, you have these named projections which behave really nicely, and there's some principles for records that are, there's apolil, I think, for records that makes them behave sort of better in some cases, I suppose.
Inference cases, so when Agda is trying to infer the types, sometimes mapping things in records, it it basically remembers, it remembers these parameters in more cases. Doesn't erase them as eagerly.
Just a quick question about that, which I hadn't paid attention to before. I didn't realize you could declare a precedence of 0 for an
You can
index.
declare a precedence of -20 or -20.01567.
Okay,
It's literally a linear order.
fine.
There's nothing special about.
There's nothing
There's
special
no
about-
privilege values. for
There's
that.
no bottom.
There's no
There's no
bottom.
bottom. Yeah.
Yeah.
Wow. Yeah. Cool.
Yes.
Okay, and so
There is another question about this, and if you center the screen, you can see the comparison between the record declaration and the analogous data declaration. Is that constructors of data types can be overloaded, they can be reused because but field names, I think, cannot. Is that right?
That is true. Yes.
Yeah.
Yeah. So if you declare more than one record, if you declare more than one record with the same field names, then Agda will not be happy.
Yeah.
But in many cases, we declare constructors and data types with duplicate names, and Agda, in many situations, will be able to disambiguate them directly. I don't know why that is. Well, I guess they're very different things, right? Is that the constructors are, I mean, field names.
Oh, projections.
Field names are projections and constructors. Yeah. So does this definition of isomorphism make sense to people?
So it's a definition, and it's one that's very much tailored to the equality, right? So it is.
Yeah, it's not parameterized on how A and B understand their values as being equal.
Yes.
Yeah.
So this is very much,
Yeah.
With relation to the equality that was defined in the earlier chapter. And this is something that is not really how the standard library operates in most cases.
So the standard library usually bundles. Well, yes. So maybe we should give an example of a type where you would want. So propositional equality is that the term is exactly syntactically equal.
Yeah. And one example of problematic type is higher up.
It's higher up, which is
the function space.
Oh, function space, yes.
Right. So extensionality, we can postulate it, but it's not there. And so, one way to define equality for functions is to say, it's pointwise.
Two functions are equal.
So functions are equal if they're equal for all arguments. The results are equal for all arguments.
And that's
So on this definition, we couldn't prove an isomorphism between nat cross nat arrow nat and nat arrow nat arrow nat, because the notion of equality on those two types
is not
is a bad fit
yes,
for this definition.
propositional equality. So maybe.
Oh no, no, wait, that's not true.
No.
Go back. Precisely because from to and to from are phrased extensionally, it's not equality on functions, it's equality on the images of functions. I think probably you can do that, because these are somehow extensional definitions. Right, these are saying that the compositions of functions are extensionally equal to the identity. So for sure, it's not borrowing any richer structure from A and B themselves, but from the point of view of function composition, it's respecting extensionality, I think. Conjecture.
That sounds plausible. The go-to example that I tend to use in that for where you might want a separate notion of equality is rational numbers, which is in the standard library, right? Which you
Or
can
integers.
or integers. Ooh. Oh, yes, sure. If you have plus and minus 0.
Yeah.
Yeah. So okay. So yeah. I mean, rational numbers. There's a rational number 4 over 2, right? Is equal to 1 over. Is equal to 1, right? Or 1 over 1. No, 4 over 2 is equal to 2 over 1, right? Okay. But they're not syntactically the same, right?
Yeah.
Yeah, so like with many of these types, there's a question, right? Because some of them do admit representations that are actually equal. Rationals do, right? You can normalize.
Yeah.
And integers do, but this is not really how you usually define them in sort of in classical mathematical textbooks, where they would be, you know, abstraction classes of subtraction or something like that.
Yeah.
Right?
Yeah.
And the rationals would be, you know, equivalence classes of division.
So, for example, this is the definition of unnormalized rationals in the standard library. You have a numerator. Oh, sorry, yes. Is that better?
That's nice for me. Thanks.
Yeah.
Yeah.
So you have a numerator. Ooh,
No.
sorry, it's jumping around. You have a numerator and a slightly ugly thing, but I may be getting around to change in version 2.0. So you have a denominator minus 1, which basically ensures that your denominator is non-zero. It's a natural number.
Yeah.
And then we actually have to define a custom equality, right?
Yeah.
Which is the kind of usual one that you learn in school, that two fractions are equal if when you cross multiply.
Yeah.
So, for instance, whereas you might want to use that equality in the isomorphism, but you can't. An alternative way of defining this, which is often much nicer to work with, alternative way of defining rationals. Oh, I hate that one. Is if we go to.
Oh, it says your screen sharing is paused.
Oh, right on pause, resume share. Sorry. If we go to rational.base, so not the unnormalized versions, okay, the constructor for normal rationals, right, actually has the same fields, numerator and denominator minus 1, but it also contains a proof that they're co-prime.
Right.
So whenever you are constructing a rational number, you have to construct it in its lowest form, right? At which point, if you scroll down here, okay, we do still have this alternative definition of equality, just in case people
But no
would like to
comment.
But it actually coincides. So you can prove that whenever two things are propositionally equal, then they fulfill this relation, and then so there's a tension, right, between you can either include proofs in your data type that collapse everything down, so you don't need equalities, you don't need custom notions of equality, or you can have multiple representations, but you can have your own custom notion.
And of course, there's limits in the sense that once you go to reals, you're not getting good stuff out of your standard definition of equality either.
Yes, yeah, because a real isn't actually really representable. It's always going to be some limit of some approximation function or something.
Yeah.
Well, arbitrary.
Yeah, I mean,
arbitrary real. So let's have a look at the standard library's definition of isomorphism instead, which is whoa.
And while you find that, I'll just make a comment that because this is PLFA, all the objects that would live in types A and B for isomorphism are typically syntactic tree-like things. So for them, the natural notions of equality are the structural ones which do coincide with propositional equality.
Yes.
Because when we do things with syntax, we tend not to consider non-trivial quotients.
Yeah.
So we work with bare trees. That's not entirely true, but I think it's largely true for the purposes of the book.
And I think, this is also true that often when we work with programming languages, most of the things on which we consider equality, possibly excluding function spaces, the equality is decidable, which makes, it makes many things much simpler in terms of, constructive type theory. Certain things that would be axioms otherwise are actually provable, these sorts of things, particularly things that relate to equality.
So this is the equivalent definition. We don't tend to use the term isomorphism is very overloaded in many different contexts. So we tend to avoid it because massive arguments about no, this should be isomorphism or that should be isomorphism. So this is a notion. So again, if we compare it, you notice that we still have the same. Ooh, okay, I've actually got a pull request to rename these F to and from right open this moment.
Yes, indeed, which is quite a nice request, in fact. Yes, F and G.
F and G are not so nice.
So that's the comment about field names must be unique.
Yes.
So once you've given away to the system the names F and G, you've tied your hands for reasoning about arbitrary functions.
Yes, if this is in scope. Yeah.
Yeah.
Okay, so you have the same functions, but you notice we don't have. Oh, it's actually quite different. Okay, so the types here are actually really. No, this isn't. Hang on. Yeah, no, okay. So the types here are a little bit different because this says if you apply from and to, you get the same thing as you started with, and the same thing with to and from. This one says that if you have two things that are equal under equality on the first element, on the first type, so A, then you apply F and they're still equal under this, over the results are still equal with some second notion of equality. And the same thing with the other function in the other direction. So you can derive their notion of isomorphism from this. Right.
Yeah, because if you compose the functions and compose the proofs Cong1 and Cong2, they're saying if x is equal to x, then f of g of x is equal to x, essentially.
But so where do these equalities come from, right? We've just seemed to have magicked them up in this definition. And actually, they come from all these definitions. So all these different function definitions of different types of functions. So equivalences, left inverses, bijections, surjections, injections, just plain equality preserving functions, are all parameterized, all live in this nameless module, and they're all parameterized by two, not sets A and B, but these records called setoids, which in this case are named from and to. Sorry. What is a setoid? Well, a setoid is simply I wish I could jump. I wish.
You can't jump in the HTML.
No.
It generates HTML, but it doesn't hyperlink.
No, it should do. Anyway, what is a setoid? It is.
Binary.
Yeah. Binary bundles. Is a setoid a partial setoid? No. Okay. So a setoid is simply some type, which is called carrier. Again, it's another record, equipped with some equality relation, and a proof that the equality relation is an equivalence. So this is a kind of generalized notion of a set, right? Of a type with some arbitrary notion of equivalence over it that you don't know about, but is going to provide its own notion of equivalence.
This is the closest we get to quotients in
this particular branch of type theory.
Agda or in Koch, I think.
Yeah. Yeah, so this is another record. What else is interesting about this?
Well, I suppose, you know, this is how Agda structures, like the Agda standard library, structures a lot of these types with structure, right? So here we have three things. We have carriers, we have operations on them, and we have proofs. And quite often there's like pretty involved structure in terms of how standard library defines these things. First off, packaging away the propositional structure, the proofs, because you see we don't have reflexivity and symmetry and transitivity as elements there. We basically just have a package that says equivalence, right? And then packages away the operations that you might want on these, and then also the carrier types.
I'm not really sure why I'm exploring this on GitHub. If I explored it in code, it would actually have links up here. So,
well, partly because PLFA is on the web, and
yes.
so the impedance mismatch is a bit punchy.
Where's PLFA gone? Oh, here.
Yes.
Okay. Zoe, do you have any questions?
No, other than just
Comments?
I know they become much more interesting when you enable cubicle.
Yes.
Yes.
So cubicle it changes type theory, which Agda is based on, and allows much more. I feel ill-equipped to describe exactly what it does, but
Joy and pain.
joy and pain. So it's much more of a cutting-edge type theory that yes, people haven't more. You can prove a lot more exciting things in it, but it's working with it concretely is much less ergonomic.
So one thing we've emphasized is that for triple bar equality, there is only one proof, REFL. So you can pattern match on it, and it will always be REFL if you have such a proof, and that will force the left-hand side and the right-hand side to be understood as being really identical by the type checker. When Zoe moves to cubicle, that whole space of proofs of equalities explodes into 1,000 pieces with their own very complex and subtle geometry, which is very interesting, and, for example, connects with stuff that Christian Zeman does with high energy physics and higher dimensional structure there. But definitely not for the faint-hearted. So I know what's going on, but I rely on Zoe to teach me what's going on, basically, because I don't always understand it.
Okay, so to get back to PLFA, so this is the equivalent definition in data structures, as mentioned. And the crucial thing is that you would manually, records provide all these projection functions for free when you define the record. So you can just call 2 on an equivalence and it will get it automatically. If you define its data structure, you'd have to manually define each of these functions with, all the gnarliness that goes with that. And records also give you a nice syntax for constructing them as well. Instead of like in Haskell where you'd, you have records in Haskell too, but instead of the data constructors that we've been using in Haskell where you just manually provide the arguments in the right place, records allow you to actually do named, provide them names as well, which can make for more readable code.
Yeah, you can actually have both, right? For records, you can have named constructors that behave sort of more like the constructors for data types too. Okay. So we'll do.
So, yes, you would really hope that our definition of isomorphism is itself an equivalence relation. So it represents an equality. And this is how you'd prove it. You'll prove reflexivity. So 2 becomes the identity function. From becomes the identity function. And obviously any element is always equal to itself. So the proofs that they commute, that from and to commute, is just reference.
And it's particularly perverse / eccentric / I don't understand why they've chosen to write one clause pattern matching lambdas here rather than what we would write with just a lambda term.
Yes. So, but the brackets mean that they could actually pattern match on the x and y arguments coming in.
But they don't.
But it would be impossible to, right? Because you don't even know what type of A. You couldn't pattern match on x and y because you don't know what A is.
Yeah.
So you could actually just remove these curly braces entirely. And it would still work. Symmetry is very similar.
Yeah.
To record becomes a from record. The to function becomes a from function. The from function becomes a to function. And then the proofs likewise swap around.
Yeah, so it's sort of interesting that it does fiddle with the structure, right? It's not just the proofs; it's really.
It's rearranging things.
Yeah, so here it's symmetry because you have to change the like exchange the functions, right? And the transitivity you have to compose, and the identity you did pick the identity isomorphism, right?
Ooh. Whoa,
Wow,
what are they
that's
doing here?
tasty.
This seems
transitivity.
overkill.
This is very tasty. Blimey.
Ah, so they're using equational reasoning here.
Yes.
So if you, so the functions, as you'd expect in transitivity, if you've got an isomorphism from A to B and from B to C, then you just go, you use the first one to go from A to B and the second one to go from B to C, and you compose them together. The proofs, really the entire proof is summed up in this line here.
Yeah.
That you apply congruence of this thing. Everything else here, if you notice these, oh no, that's not true.
No,
that's not true. There's
true.
another line here. Okay.
No, you have to use congruence to expose an equality.
Yes.
Yeah.
Yeah. And then you have to use transitivity of propositional equality. But yeah, these are showing the intermediate terms, and then as before, these are showing the proofs between the transformations between each intermediate term. Yes. I don't think there's anything super special about these proofs. It's sort of munging.
Not very much. Well, we have projections from the records a lot, right? In the sense of you're using. So here it's the functions, right? But then you have the from to of the second isomorphism, right? Used under the from of the first isomorphism, right? That's probably a little bit hard to read, but yeah.
So part of what I think makes that look especially unwieldy is trying to do everything inside the record declaration.
That's true.
But you could have a where clause after the final curly brace and do a lot of additional lemmas and proofs if you needed to break up the flow.
And you could also define this by defining the projections, so sort of by using copatterns. But do we want to look at that?
Sure.
Because this is
yeah.
not what you'd get if you sort of just started writing the proof, right?
No, this
And
is
sort of doing it in the natural interactive fashion.
no, it
This
doesn't
is
generate.
not what you'd get.
I mean, it doesn't generate copatterns for you automatically unless you turn it on specifically. It will generate this record declaration.
Will it?
Yeah, it will.
If you split on, if you do define transitivity over A isomorphic to B and B isomorphic to C
Yeah.
is a whole, and then you split on the result.
Yeah, it'll give you a record.
Yeah.
It will do.
Yeah.
Well,
Yes, 100%.
it didn't
Ooh.
do that for me
Ooh,
last time I tried.
Ooh.
okay.
Well, I mean, not for this particular example, but I was doing something similar and it didn't.
Okay, let's give it a go. Let's test that hypothesis.
Yeah.
Source. Where am I? Vehicle. No, let's go somewhere with. Oh, test that. Really should clean up after myself. Oh, this is from last week.
Well, not, but
Yes. Let me work. We shall see, and you want to.
well, whichever. The reflexivity
Well,
is,
let's
is
do-
simpler, right?
Let's do transitivity. Okay, so you're saying if we put a question mark there and we ask Agda, okay, what's the next step in the proof?
Split on the result.
Sorry, split on the result, like
Control C, Control
refine, control,
No, Control C, Control.
Control C, Control R.
No.
So
if you
Control
do
C, Control R.
Control R, yes. If you do Control C, I think, or Control whatever is the split.
Split on empty to split on result. Ooh,
So what
okay.
happens here is it
Yeah.
says, so I said, yeah, okay, how is the result formed? Try to split on the result. And what it says is, I'm trying to define a transitivity, an isomorphism between A and C, and it's a record. So if you define how all the projections work, will be done.
So if we, for instance, put this in, yes, okay.
It's probably not important.
Yeah, and then you can define each part of a record separately if you want.
Yeah.
There's no difference between this. There's no.
It's the same definition, it's just a different presentation, right?
So this begin syntax that we saw.
Yeah.
It's the book was defined.
Yes, it is from the book.
Okay.
Yeah.
It's from the book and it's also in the standard library, and it is very useful if you have long chains of equational reasoning to do.
Yeah, and in the book you can see that basically you can define it for lots of
In fact,
relations, right? So both for equivalences and orders, there might be some differences.
so the standard library has a super souped up version of it, which works over. You can use it to define equality. You can use the same syntax to define chains of equalities, chains of inequalities, chains of strict equalities, and mix them all together. And it all works magically. The syntax they use here, I really hate mixing. I always think it's much cleaner if you have the space to write them, and then it's actually readable. And then you have the proofs down the right hand side and the terms down the left hand side, which is how we try and write it.
But yeah, this
So
is
when that notation was first introduced, so it's a product of the Eindhoven School of Programming. I think Wim Fine was the first to write proofs in that form. it's a very deliberate design choice to separate the reason why an equation holds from the terms. So indeed, to have them laid off on separate lines and indented by the constructor. So that's more orthodox Eindhoven style than Agda style.
Sorry, this is more.
This is more Eindhoven style.
Okay. Yeah.
But not everyone is baptized in that religion. And I've only recently adopted it, but sometimes the terms are boring, but the reasons are interesting.
Yes.
Yep. Which means you could actually just drop the terms altogether and just say trans of that thing and the other. And it will also work, and it will be completely unreadable, but if you're just hacking something together, it's
well, not completely so. What I'd be very interested, just as an example of this proof, is what would happen if you replaced all the terms with underscore, but left only the reasons in.
So
Is the type checker good enough? So,
no, so we've got it open. Okay, so well, it's not gonna. Oh, yeah, no, it should do. Okay, so James is saying if we replace, say, we're not going to tell you what the actual terms are with. Here it is.
pretty sure it works, yeah.
So because the proofs dictate the type so strongly, the proofs leave no choice to Agda as to what the the types of the individual steps are. Sorry, the objects of the individual step are.
Yeah, if you tell Agda to try to infer what it's rewriting under, it might die, right? If you change the from a here, if you turn this into an underscore, yeah, we'll see error, right? It can't figure out that what we're trying to do is rewrite under the first direction of the first isomorphism.
But but I don't think. I mean, it wouldn't work even here. Even if you, it's not. It's just the case that it doesn't know what the proof of equality. It doesn't know what the proof is, right? Like it can infer what the elements it's proving. It's trying to prove are equal, but it can't infer the proof. So.
Yes, the type checker isn't psychic, but proofs often contain more information than terms, and therefore allow you to.
Yeah, so this is really just trans of this proof and the other proof.
Yeah, if we look at the definitions of these, if you look at the definition of this quantity operator, it just gets translated to a simple trans. And yeah, dot becomes referral, as you'd hope. And then I think begin is the identity function. So if you actually take out begin is just syntactic sugar. You don't actually need it at all. That's,
I think there's like some cases where it changes the way things pass, but that's just a question of precedence, right?
No, so begin actually does some cleverer things. If we go to triple reasoning, do we want to explore this?
Well, so the triple reasoning is the next thing that's defined in the book, right? For the isomorphism.
No, they don't go anything.
Don't
they do.
Oh, yes, they do.
Oh, they define it separately. Okay, yeah. So that's.
Higher up.
Yeah.
And here we
Okay, so yeah, let's cover this first and then go back to how the standard type grid does. So they define this reasoning syntax, especially for propositional equality before. So they use the explicit proofs of referral trans. So here they're showing, okay, well, we could define it. We could define it especially for isomorphism equality, for this notion of equality, and they define it in exactly the same way. Becomes trans. Begin is the identity function. The equality step is the transitive operator, and the conclusion is Raffles.
Yeah, and since we don't use symmetry anywhere in this syntax, of course, this also works for orders.
This also works for, yeah, orders. So we then go on to define embedding, which is weaker version of an isomorphism in one direction.
And I find it a bit weird, the definition, because it requires you to have functions in both directions, which means that the empty type does not embed in anything, which I find weird, but.
But then you can show that it's reflexive, it's transitive, as before, very similar proofs, and that it's antisymmetric to a certain extent, requiring, yes, requiring that the functions are pointwise. No, yeah, the functions are actually propositionally equal, but actually equal. So this is a very.
They assume extensionality.
Oh, they do assume extensionality equal earlier. So okay.
So basically, we've assumed that the functions are equal when they are
equal
sort of in the natural extensional way. And here you have to assume, yeah, yeah, you do get anti-symmetry if this is actually the same isomorphism, right?
Okay, so we then show, yeah, again, you can define exactly the same trick. Instead of having equal signs everywhere on the reasoning, you can just have, you can substitute any symbol there, and you can do a chain of proofs of embedding. So, and this works for any order. I mean, this trick works for any orders over any arbitrary sets, and there's nothing special about embeddings or isomorphisms. So, oh, there's another exercises. Yeah, so a standard library obviously doesn't want to define a special reasoning for every single type. Doesn't want to define it over, isomorphisms, over embeddings, over less than equal to natural numbers, less than equal to for the integers. It just wants to define all the reasoning once. So let's go somewhere there. We have a relation.binary.reasoning module that defines reasoning over various arbitrary structures. So Acetoid reasoning is the one that reasoning over propositional equality. So reason, like the equivalent to reasoning over propositional equality, it is, but works over arbitrary setoids. So you just have to provide a setoid and it will give you reasoning combinators for any setoid. And likewise, we have ones for partial orders, pre-orders, strict partial orders. The interesting thing is that actually the ones for instance, partial orders work for, hang on, let's go back to the test. Maybe a demonstration is. So that's open import data.nat.properties.
3 hours later.
And then we're going to open.
We've been making it better.
It's getting better.
It is getting better.
Oh, no, it's that one. I have to content. Okay, what have we got? Yes, okay. So if we want to go 3 is less than equal to 5, then so less than equal to reasoning and data.nat, the properties imports this base reasoning module and just instantiates it with a proof. But the clever thing is that, okay, so begin, you can have 3 less than 5, right? So you can prove inequalities with it, but you can also prove strict inequalities with it. With, hang on, let's give an example of that. 3 is less than equal to 5, so let's go again. 3 is less than 4 is less than, sorry, 5. QED, but you have to do begin strict. Sorry, that's 2. Okay, so that seems, so we just changed the begin thing and we changed things, but you can also do things, you can mix and match them, and it's clever enough to notice that as long as you have one strict, you're equal. But for instance, this will pass as well.
Oh, wow.
Okay, so
this is probably why you can use multiple strict equalities when you're proving a strict equality, where sort of the natural transitivity would have a weaker relation if it could, right? So weak on one side, strict on the other side, because strict matters, right? Strict implies the non-strict.
yeah, and you can embed. So the reasoning combinators are really quite powerful in terms of writing proofs, and you can mix and match them, and that is because it's all the magic in these begin in this case is no longer the identity function.
Yeah.
So begin takes the proof that you've constructed so far and the rest of it, and then uses the fact that it's decidable whether it is strict or non-strict or is an equality, and actually runs a decision procedure to see if you've constructed something of the right form.
That's fancy.
Yeah. So there's a long way you can go in making your fancy syntax even cleverer. And yeah, it's all definable in Agda. Like none of it's built in.
Yeah, so in practice with these equalities, me coming from more of a tactic-based theorem provers background, equalities is where, and equality rewriting is where I get a little bit annoyed with writing all this, particularly if it's a large term, and particularly if I have to rewrite on a lot of structure, because as we've seen, Agda can't just say conc underscore. You have to tell Agda where to rewrite. There's a rewrite thing, right?
No, so version 2 of the Sun library is going to have Kong exclamation mark.
Yeah.
And you're just going to type the proof there, and you're just going to write it, and it will automatically infer where to put it.
I will be much less annoyed.
Yes. So yeah, Sun version 2 of the Sun library is going to be sweet. Yeah.
And it's definable, like nothing. Just clever use of inference that's already there.
No, so it's a tactic.
Okay.
It's uses anti-unification to locate where in the term that you want to apply the congruence proof.
Right. Okay.
But yeah, it'll have it as a default.
Yeah.
Okay. Yes, and they give the locations. Oh, they say it's an inverse, not an equivalence. Okay, they give the locations and it's or they give the old ones. Oh, we're gonna have to update that.
They
give the very old definitions. Right. Well, that's the end of the chapter.
And we're almost at 12.
We're almost out of time.
Yeah. So shall we look at the
table of
contents and then see what we should, like how we should proceed, because there's
oh gosh, we still have quite a lot of part 1, don't we?
Yeah, but that's because we're going into a lot of depth.
Yeah, which is good.
How much of this is actually interesting to people, though? Is this recapping logic, or is this recapping? Is this actually?
Well, I mean, I think it's
yeah.
It's sort of interesting how and not necessarily trivial how Agda does proofs,
Yes. Yeah. Okay.
because
I think the book is two-layered, that's why it encourages discussions. So, for
Yeah.
example, this chapter today, it was about isomorphism. In fact, it also introduced the begin syntax and so on. So it kind of, it
yeah,
tends to do several things at
Yeah.
once.
yeah.
And so you feel like, oh, connectives, who does no connectives? But actually, if they do it as in other sections, they
Yeah,
sneak
Yeah.
in other considerations, more general considerations than
Yeah.
the topic of the section in question. So, yeah, that's why I'm
I mean, I
I'm
think
worried
it,
about skipping because it
No,
seems
no.
like they introduce
No,
a
no,
lot of general stuff.
indeed, and I don't want us to skip, because in a sense, how we run this course is a prototype for things to look out for during the week of SPLV, where we hope to be running Agda tutorials for the students to work on problems coming out of some of the lectures that we'll be having.
Ooh.
Yeah,
That sounds-
I will talk to you about that afterwards.
James, you are running the course.
well, not really Agda course per
It's not an
se,
active
but
course. I've proposed a course on lambda calculus, but one way to make that go well is also to give the students tutorial labs where they can see this actually happen inside Agda.
so I think it makes sense to sort of continue going through part one, and then we should probably consider whether we want to look at questions related to